Okay, so looking at example 3.3, we are now asked to calculate the change in entropy, or the entropy change, for the surroundings. In other words, we're not looking at the system, we're looking at the surroundings. When 1 mole of hydrogen of water is formed from its elements under standard conditions at 298 Kelvin. And we're given the enthalpy of the formation of water from the resource section, which also you could have looked up yourself, but it's not given to you as that. So that's sort of given to you as a hint. And if you read section 3.4.2, then you would see that we say that the surroundings entropy change is only dependent on the heat of the system, or the heat given off by the system. So in other words, what is the heat also known as? It's also known as the enthalpy, because enthalpy tells us whether or not something is endothermic or exothermic. So in other words, it tells us whether or not there's heat absorbed from the surroundings or there's heat given off to the surroundings. And if you think about it in a logical sense, if heat is given off to the surroundings, then we should be heating up our surroundings. And what do we expect when we heat something up? We expect an increase in this order. When we have a decrease in the heat of our surroundings, or the temperature of our surroundings, if you want to put it like that, in other words, an endothermic process, then of course we are removing heat from the surroundings. In other words, we are creating less order, or more order, my apologies. In other words, we expect a decrease in the entropy. Right, so that's sort of how you need to immediately think about this question. So, this minus shows us that there is 286 kilojoules, because we're working with 1 mole, so that can immediately be written as 286 kilojoules of energy is released as heat to the environment or the surroundings. In other words, we should expect a increase in the entropy of our surroundings, and that is exactly what we see when we do the calculation, because using our equations, basically equation 3.5, which is this section of the question here, we then get that we use the definition of entropy, which is delta S is equal to the heat over the temperature, but we know in this case the heat is equal to the enthalpy, because that's the whole explanation that I've given now, or just given you. So in other words, you just calculate it and you see that is indeed a positive value, which makes sense, because if water forms, it gives off a bunch of heat, and then we suppose that there is an increase in the disorder of the surroundings, because it is a strongly exothermic reaction, and in other words, because of the heat given off to the surroundings. Right, and you might notice that I've spoken a lot more about all the things that is not present here, meaning more the interpretation of this question, and that is exactly why it is so important, because the interpretation is more important than the actual calculation. I'm not really concerned about the calculation itself necessarily. The calculation is just here for you to double check this. You might sometimes get the answer and get asked, why is this? Comment, how do we know this is in fact true? Explain at the hands of the enthalpy value or whatever, what's going on here. Right, so I hope this gave you a better understanding of what this example is trying to convey.